Okay, ready to dive into some AI research.
Absolutely, always up for that.
All right, well, get this. Sometimes giving an AI more data can actually make it, well, dumber.
Yeah, that's right.
Kind of like, studying for a test all night and then completely blanking when you actually sit down to take it.
Haha, exactly. It seems counterintuitive, but it's a real phenomenon.
So we're going to unpack some research today that turns this whole more data is always better idea right on its head.
It's a fascinating area.
Definitely. Now, you shared some papers on precision-aware scaling laws for AI. Sounds a bit intimidating, to be honest.
It can be a dense topic.
Haha, yeah.
Yeah.
But also super important, especially for language models, right?
Right. These scaling laws help us predict how an AI model will perform, based on its size, how much data it's trained on, and even the precision of the numbers it uses in its calculations.
Well, hold on, precision of numbers. I thought AI just, gobbles up data and spits out results.
Well, it does, but the level of detail on those numbers actually matters a lot.
Okay, I'm intrigued, but I'm also a little lost.
Think of it this way, like, if you're drawing a portrait, a rough sketch will give you the basic idea, right? But a high-resolution photo, that captures every wrinkle and freckle.
Ah, okay. I see where you're going with this.
AI kind of works the same way. The more precise the numbers, the more detail it can capture and process.
So more detail equals better performance. But you also said that sometimes more data can be bad.
That's the tricky part. There's a balancing act. One of the things explored in the research is something called post-train quantization, or PTQ for short.
PTQ, got it. What is that exactly?
Basically, it's like shrinking an AI model. Makes it run faster and use less space. But sometimes that shrinking process loses important details, especially if the model was trained on a massive amount of data.
Wait, so a model trained on tons of data could actually perform worse after being shrunk with this PTQ thing?
That's exactly what the research suggests.
That just doesn't make sense. Why would that happen?
Imagine you're stuffing a suitcase, right? The more you cram in, the more compressed everything gets.
Right.
If you then try to squeeze it into an even smaller bag, you're more likely to damage things, break things, lose things.
Ah, I see. So it's not just about the quantity of data, but how that data interacts with the model's precision.
Exactly. And that's where these scaling laws come in handy. They help us predict how these factors play together and find the right balance.
So it's like a recipe for building efficient AI. Speaking of recipes, what about training AI in lower precision to begin with? Does that help?
That's called quantized training, and it's a hot topic right now.
I bet. What have they found?
Well, it turns out there's likely an optimal precision for training. Probably not the standard 16-bit precision we use today, though.
What is it then?
The research suggests 7 or 8 bits might be the sweet spot.
So it's like finding the right resolution for your AI's training process.
Exactly. Not too detailed, not too blurry, just right. It's about finding that Goldilocks zone to balance performance and efficiency.
This is really interesting stuff. It makes you realize how much complexity is hidden behind AI development.
It is, and it's only getting more complex.
Now, you mentioned something about training models in a series, like the Llama or Gemma families. How does precision play into that?
That's where things get really interesting. The research suggests that when you're training a series of models on similar data, well, the optimal precision actually changes.
How so?
It depends on the amount of data you're using. More data might actually require higher precision.
Wait, wouldn't more data usually mean we could get away with lower precision?
It seems counterintuitive, right? But remember, we're talking about models that are already trained on massive amounts of data.
Okay, yeah, I see.
Think of it like this. The more knowledge you have, the more nuanced your understanding of the world becomes.
Okay, that makes sense.
Sometimes you need more precise tools to work with that complexity.
Ah, so it's not just about the quantity of data, but also how deeply the model is absorbing it.
Exactly. Precision becomes a way to fine-tune performance when you're dealing with these massive data sets.
This is blowing my mind. So there's no universal answer for optimal precision. It's all about context.
Precisely, and that's what makes this research so valuable. It challenges the one-size-fits-all approach and encourages us to think more strategically about AI development.
Before we get too lost in the nuance, can you remind me what the big takeaway is here? Why should our listeners care about all of this precision stuff?
That's a great question. The key takeaway is this. Precision isn't just a technical detail. It's a fundamental lever that influences AI's capabilities and limitations.
So I need to pay attention to it.
Absolutely. By understanding how precision interacts with data and model size, we can build more efficient and effective AI systems.
That makes a lot of sense. So we've kind of laid the groundwork for understanding precision, PTQ, and quantized training. But how do we actually use this knowledge? Where does this scaling law you keep mentioning fit in?
Ah, yes. The scaling law is where it all comes together.
Okay, tell me more.
Imagine having a single equation, one that predicts how a language model will perform based on all these factors: size, data, training precision, and even the precision it's reduced to afterwards.
That sounds incredibly powerful.
It's a huge step forward. This unified scaling law gives us a framework for making more informed decisions about how we design and train AI models.
I'm already imagining the possibilities, but before we get ahead of ourselves, let's dive into the details of this scaling law. How does it actually work?
That's a great place to pick up in part 2.
Okay, so in part 1, we talked about precision, PTQ, and quantized training. But you also mentioned a scaling law that ties all of this together. What exactly does that mean?
It's basically like a master equation. It tells you how a language model will perform based on its size, the data it's trained on, and the precision that we've been discussing.
So instead of just kind of throwing more data at a problem and hoping for the best, this scaling law helps us make smarter decisions about how we train AI.
Exactly. It's about being strategic and understanding how these different factors, they all work together.
All right, color me intrigued. Break it down for me. How does this scaling law actually work?
Okay, so it all starts with the traditional scaling law, the one that relates model size and data volume. That's been around for a while.
Right, like the bigger the model and the more data it's trained on, the better it will perform.
Right, but this new scaling law, well, it takes it a step further. It incorporates this concept of effective parameter count.
Effective parameter count. That sounds a bit technical.
Yeah, but bear with me. Think of it like this. The precision at which you train a model, it actually impacts how much information each parameter can hold.
Okay, I think I'm following.
So let's say you have a model trained in lower precision, right? It might have the same number of parameters as a model trained in higher precision, but its effective parameter count is lower because, well, each parameter is holding less information.
So it's like adjusting the model size based on how much detail each parameter can handle.
Exactly. It's a much more nuanced way of looking at things. And then, well, there's another term in the scaling law. This one accounts for the performance hit you might take from post-training quantization.
Right, because shrinking a model can sometimes lead to information loss, like squeezing all your clothes into a smaller suitcase.
That's the perfect analogy. So this last term in the scaling law, it factors in both the training precision and the final precision you end up with after quantization.
So it's like this comprehensive view of how precision impacts performance throughout the entire development process.
Exactly. That's the power of this unified scaling law. It brings everything together.
This is starting to feel like a real revolution in AI development. Instead of just blindly experimenting with different configurations, we now have, well, a roadmap for building efficient and effective models.
I think that's a great way to put it. And this roadmap has the potential to save researchers and developers a ton of time and resources. No more guessing games.
Let's get real for a sec, though. Can we really trust these predictions? I mean, are we talking about a crystal ball here?
Well, like any scientific model, we have to acknowledge there are limitations. This scaling law is based on experiments, right? And it might not perfectly capture every little nuance of AI training.
So it's more of a guide than a set of hard and fast rules.
I think that's a good way to think about it. But even with those limitations, it offers incredible value. It gives us a framework, a way to think about these really complex relationships.
And I imagine as more research is done, these scaling laws will just get better and better, more accurate, more reliable.
Oh, absolutely. This is really just the beginning.
Exciting times. Now, let's shift gears and talk about some real-world applications. You mentioned that this research could be a game changer for AI development. Can you give me some specific examples?
Sure. One that immediately comes to mind is edge computing. All those devices that are becoming smarter and smarter, like smartphones, smart speakers, even self-driving cars.
Right. And all of those devices need AI that's both powerful and lightweight.
Exactly. And that's where post-training quantization becomes really valuable.
Because it shrinks those AI models down so they can run on devices with less processing power.
Right. But we've learned that shrinking a model, especially one that was trained on a lot of data, can really hurt performance.
So how do we balance those competing needs?
That's where the scaling law steps in. It helps us predict how much performance we might lose due to quantization, and it guides us in choosing the right model for the job.
So maybe instead of automatically using the biggest, most data-hungry model, sometimes it's better to choose a smaller one that will actually perform better after it's quantized.
Precisely. It's all about making those smart trade-offs.
Makes sense. What other applications can you think of?
Another big one is sustainable AI. As AI models become larger and more complex, training them takes a lot of energy. It's becoming a big concern.
It's true, those massive AI models can have a huge carbon footprint.
And that's where understanding precision and using these scaling laws can make a real difference. We can potentially reduce energy consumption without having to sacrifice performance.
So we could actually use these scaling laws to make AI development more environmentally friendly.
It's definitely a step in the right direction. By being more mindful of precision, well, we can help create a more sustainable future for AI.
I like that. We're not just talking about performance here, but also the broader societal impact of AI.
Right. These considerations are becoming more and more important. And these scaling laws, they provide a framework for developing AI in a more responsible and sustainable way.
But what about those limitations we discussed earlier? How do those factor into real-world applications?
It's really crucial to remember that these scaling laws, they're based on specific architectures and data sets. They're a good guide, but we can't blindly apply them to every situation.
So there's still a need for good old-fashioned experimentation and fine-tuning, even with these scaling laws.
Absolutely. These scaling laws, they're a tool, but they don't replace the need for careful engineering and expertise. Humans are still in the loop.
It's like having a map, but you still need to know how to navigate the terrain and adjust your course along the way.
Exactly.
This has been an awesome deep dive into precision and its impact on AI. We've covered so much, from the surprising fact that more data can sometimes make AI worse, to the idea that we might need to rethink how we approach precision as AI continues to evolve.
Yeah, it's been a great discussion.
But there's one more thing. You mentioned something earlier about a bigger question lurking beneath all of this.
Yeah.
Something about the fundamental limits of precision in AI.
Ah, yes. You see, throughout this whole conversation, we've been focused on the technical details, how precision impacts performance and all that. But, well, there's a bigger question here. What are the fundamental limits of precision in AI?
Whoa. Okay, now we're getting philosophical.
As AI models become more sophisticated, more data-hungry, well, it makes you wonder, will we eventually hit a wall with precision?
You mean a point where the need for super precise calculations actually starts to hold back progress?
Exactly. Could there be a limit to how much information we can squeeze into these models? A point where chasing ever-increasing precision actually becomes counterproductive.
It's a mind-blowing thought. It makes you wonder if there's some fundamental constraint we haven't even considered yet.
It's definitely something to think about. And it highlights how important it is to not just focus on those small incremental improvements in AI. We also need to be thinking about these bigger questions, the nature of intelligence, the limits of computation.
Wow, this has been a real eye-opener. I feel like I have a whole new perspective on AI and where it might be headed.
Me too. It's so fascinating how these technical details can lead to such profound questions.
Absolutely. Let's let all that sink in for a bit, and then we'll come back for a final recap and some parting thoughts.
Sounds good to me. I'm looking forward to summarizing our journey into the world of precision and its impact on AI.
All right, time to wrap up our deep dive into precision and AI. My brain is still buzzing from all this.
I know, right? It's really fascinating stuff.
So we started by exploring, well, kind of the technical side of precision in AI, but then we ended up pondering some really big questions about the very nature of intelligence.
Yeah, it's amazing how these seemingly technical details can lead us to such profound insights.
So we talked about the challenges of post-train quantization and those surprising findings about optimal training precision. And of course, we can't forget the revolutionary potential of these new scaling laws.
Right, those are game changers for sure.
But honestly, the question that really sticks with me is this: are we approaching some kind of fundamental limit in AI? A point where, we're chasing ever-increasing precision actually starts to hold us back.
It's a really intriguing question.
It makes you wonder if there's some kind of inherent trade-off between precision and complexity, or maybe even between precision and creativity.
There's definitely some interesting research suggesting that certain aspects of intelligence might actually benefit from a little bit of imprecision or randomness.
Like the human brain. It's not perfectly precise, but it's capable of some pretty amazing things.
Right. Maybe there's something to be said for embracing a bit of fuzziness in AI, allow for more flexibility, adaptability.
It definitely challenges that traditional view of AI as like this perfectly logical and deterministic system.
Exactly.
What if we could create AI that can adapt to changing environments, come up with new ideas, even surprise us with, its ingenuity?
It's an exciting possibility. But it also raises those big questions about what it truly means for a machine to be intelligent.
It seems like we're entering this uncharted territory where that line between human intelligence and artificial intelligence, it's becoming increasingly blurry.
Yeah, and that's what makes this research so fascinating. It not only gives us these practical tools for building better AI, but it also forces us to really think deeply about the nature of intelligence itself.
Well said. So, for our listeners who are still processing all of this, can we offer some key takeaways? What are the most important things to remember about precision in AI?
Okay, so first and foremost, precision matters. It's not just some minor technical detail. It really shapes what AI can and cannot do.
Precision is power.
Exactly. But second, there's no universal answer for what the optimal precision is. It all depends. The specific model, its purpose, the resources available. Context is everything.
So it's all about finding the right precision for the job. And third,
and maybe most importantly, as we push the limits of AI, we need to be open to the possibility that chasing ever-increasing precision, it might not always be the best approach. Embracing some degree of imprecision or even randomness could be the key to unlocking even greater flexibility and adaptability in AI systems.
it's almost like we need to find that balance between precision and a little bit of chaos.
Exactly. It's that interplay between order and disorder that often leads to the most interesting breakthroughs.
This deep dive has been a real eye-opener. Thank you so much for guiding us through this fascinating world.
It's been my pleasure.
This is The Deep Dive, signing off. But the conversation continues. Keep exploring, keep questioning, and keep pushing the boundaries of what's possible with AI.